The DY,
You want to do an example there? The DY stuff? I guess. I guess we can do that. You guys are put perspective for me. DY stuff. Okay. Let's not make up a goofy example like I did last time. And something that's a little bit more appropriate.
right? We're gonna do like all the way to extrema right off.
Yeah, 4.1, I think, is where we're gonna go. Right? Our test is 1 week from Wednesday. I'm gonna find something here that you might want to do. Okay. Here's one. This is 3.7, I think, or 3.8, 3.8. Use a linear approximation. Good marker. It's a linear approximation to estimate the amount of paint in cubic centimeters needed to apply a coat of paint .07 centimeters thick. To a hemispherical dome with a diameter of 35 meters. Is that a mean one to start out with? I'll draw a picture. I'll draw a picture and everything will make sense. So we got something that looks like a half of a sphere. With a diameter of 35 meters. We're going to put a coat of paint on it that is 7/100ths of a centimeter thick. So I'm going to make it kind of thicker so you can see it. No, that looks kind of goofy. All the way around that. And so what we're asked for essentially is to find the overall volume of paint, right? because we got cubic centimeters. So I estimate the amount of paint in cubic centimeters. So I see centimeters cubed, that's telling me volume. Estimate the volume of paint put on this hemisphere. And the hemisphere is a fancy way of saying a half sphere. So we're estimating a volume. What's the formula for volume on a sphere? Anybody know? 4/3 pi r cubed. The volume of the paint is 4/3 pi r cubed. Now let's figure out this thing here.
Are we using 0.07 or 0.7?
0.7. I've transposed my zeros. So what do you think that 0.07 represents? Let me draw the whole sphere because my picture I think looks stupid. All right, so we're going to put some paint on there, but we're only going to put paint on the whole sphere. So we cut it off right there. Now it looks okay. Just draw it in 2 dimensions. Right, here's the volume. Here's the radius of the entire sphere. So let's call that the outer radius. The inner radius is going to take us to the paint level. So that 0.07 is the difference between the 2 radii, right? That's going to be a change in R. That's a delta R. So if you wanted to find out the actual volume, you'd have to find the volume of the unpainted sphere, then subtract off the volume of the sphere once you've applied that coat of paint, right? So the actual volume of paint is the volume using R0 as your radius minus the volume using the minus the inner radius. Agree? Where that inner radius is going to be 35 minus 0.07. And the outer radius is 35. So that's the actual volume of the paint is a change in V. The thing that we use to approximate the change in V is the differential in V. So we will use the fact that the differential in V approximates the change in V. Yes.
So I thought the outer radius would be half the 35.
Oh, yeah, I probably did it. Yeah, we got to cut that in half, don't we? But also the paint, I think the outer radius should be this plus the 0.07, right? Because we're putting paint on it, making it thicker.
Right.
So let's cut the radius in half, and let me put my 0.07s. Half of 30 at 5 is, let's see, 2 times 17 is 34, so 17.5. So the outer radius is going to be the 17.5 plus 0.07. And the inner radius is just a 17.5. Because the paint makes it thicker. Okay, so the differential in V approximates this exact change in V, where the differential in V is just going to be V prime times delta R. It's the derivative times delta R. Now it's just a hemisphere, so I need to cut this in half. Right? So let's cut that in half, which is going to give me 2 pi r cubed over 3. Okay with that? So we're going to take the derivative of that with respect to r to get dv. So let's see, pull out the 2 pi over 3. The derivative of r cubed is 3r squared. And then we multiply that by delta r. I cancel the 3's there. Now for r, I'm going to use the nicer of the 2 radii, which is before I add the 0.07. So I'm going to use 17.54 r, and delta r is going to be the 0.07. So I'm canceling the 3's, and we get that dv is 2 pi times 17.5 squared times delta r is 0.07. And that's going to be in cubic centimeters. Okay. So that's not an easy calculation, but it's easier than taking 17.57 and squaring it.
So do that even if the 35 centimeters.
Oh, darn it. I didn't pay any attention to that. Did I write down the 0.7? That centimeters? No, my units are all mucked up. Okay, and what do we want? We want in cubic centimeters. So I got to convert, I can't use 35. I can't use the 17.5. So this is 35 meters. And so I've got to go to centimeters. So that means I move the decimals 2 places. And so when I cut that in half, that becomes, that is our radius. So that number goes where the R is. I didn't pay any attention to that. Good eye on catching that. Move the decimal 2 places. Let me do another one.
So this was the linear approximation that we talked about, just this last section,
Yeah, there were 2 things in section 3A. There was the tangent line approximation, which was called the linearization. So this was kind of, because we're not using the entire linear approximation, we're using the change in y and not the y.
and that's the dy.
That's the dy. And I knew I wanted to change y because I just want the amount that's in the shell of the thing. So
And that's this like end part of the whole.
right. So you had one like that on web work that dealt with like the thickness of, let me see it. Let's see if I can find it. Thickness of a soccer ball kind of problem. I put that on there. problem 6. Let's look at problem 6 on your web work. It's going to be essentially the same thing. That's the definition. That's the definition of dV. dV is V prime times delta R. Okay. All right, so
that is the same as dy equals f prime a.
that's right. We have a linear approximation that looks like the equation of the tangent line. This x minus a at the end is just delta x. And this term right here is called dy. It's this thing in the box. Okay, so web work number 6 says that a soccer ball is made of leather 1 inches thick and has an inner diameter of 8.5 inches. Model the ball as a hollow sphere and estimate the volume of its leather shell. So it's almost identical to what we've done, except we're going to have an entire ball. So I'll draw that two-dimensional sphere again. And then the air part, all right? So this, we're told, is 1/8 of an inch. And we're also told the inner diameter is 8.5 inches. So the inner radius is half of that. The inner radius, half of that is 4.25 inches. And we just want to find the volume of the leather. Just want to find the volume here. So as before, if we can find the volume of the ball all the way to the exterior, counting the leather shell, minus the volume of the air part, we'll get the volume of the leather part. So the inner radius is 4.25, 1/8. Let's write them all as fractions. 4.25 is 4 1/4. So that's 16/4. That's the inner radius. The outer radius is 16/4 plus 1/8 is 32/8 plus 1/8 is 33/8. That's the outer radius. Don't know that we need that, but the volume, the actual volume of the leather, that's called the volume of the shell, is the volume of the outer, using the outer radius minus the volume using the inner radius. So those two volumes would be hard to take these two numbers and cube them and then subtract. Instead, they want us to estimate it. So again, we want to estimate this change in volume with dV. So dV is V prime times dr, or delta R. dr and delta R for the independent variable are the same. So we're going to start with the entire sphere. Volume is 4/3 pi r cubed, and we want to compute dV. Yes,
Wouldn't the inner radius be 17/4? This is 16/4.
it would be 17/4. This is 33/8. Oops, that's 34/8. So this is 35/8. Better? Thank you for catching that. That 1/8 is the delta R. And then the V that we're going to use, the nice R value is going to be this one. We're going to use that before the shell is put on. Because I got to go from the inner radius out to here, 1/8 more. So I took the outer radius, the inner radius plus the 1/8 shell to give me the overall outer radius. Right here. Okay. All right, so the definition of the differential, dV is approximator to delta V, is V prime times delta R. So V prime is going to be 4/3 pi times 3r squared times delta R. So then you choose the nicer of the two radii numbers. That's the smaller one, 16/4. And then the delta R is 1/8. Threes will cancel again. And so we have 4 pi, then our 16/4 squared times 1/8. We can simplify this a little bit. 16 squared is 256. 4 squared is 16. This 4 goes into that 8 twice. So I multiply that by pi halves. I can probably put the 2 into the 256 and get 128. 128 pi over 16. And I think that goes in there an even number of times. That's 8 pi, I believe. 16 times 8 is 128. And that would be volume, so that's going to be cubic inches. Yes.
So when we're doing just taking the derivative, we only need to put, like, only when we're taking the derivative of one with respect to the derivative of the other is when we need to include like dr or d. Like when we were doing the last section, and we have to include like dr dt when we took the derivative.
Right.
We only have to do that if we're taking it with respect to another, right?
Correct. And our independent variable is the R.
Yeah, it's only 16.
I did what?
You wrote 16/4, maybe you solved it. With 17/4.
Oh, gosh darn it. There goes all my nice numbers. Because I was looking over here. And I didn't fix it over here. Okay. So I'm not gonna do the numbers this time, I'm just gonna stop right there. 17, I don't know, 289? There, how about that? That's as far as we go. Because 289 is not even, I can't divide it. So we use the differential to, do I do something wrong again? I canceled the threes. Good eye. So that's an example of where we use the linear approximation, just the end part, to calculate the change in a y value. Sometimes we want to just approximate the entire y value. So here's how that would be stated. You have several like this. Use the linear approximation to estimate the value of 8.25 raised to the 2/3 power. So we want one particular y value on this graph. So what we're going to do is write the equation of the tangent line to this graph, the graph in general, not just this one. We're going to let f of x be x to the 2/3. And we're going to approximate the y value on this graph by using the y value on the tangent line. That's what this is. So our linear approximation in this case is going to have our linear approximation at any x near 8.25. We're going to get the value of our function at the number closest to that we can take the cube root of. I can take a cube root of 8, right? And then I'm going to multiply it by the differential part, f prime at 8 times x minus 8. That's what this is saying. That's the equation of the tangent line. So I'm going to need these two numbers. Let me go ahead and get the derivative first. F prime of x is 2/3 x to the negative 1/3, which is the same as 2/3 x to the 1/3. Now we're going to evaluate each of those at 8. F at 8 is 8 to the 2/3, and f prime at 8 is 2/3 times 8 to the 1/3. The cube root of 8 is 2, and then I square it. So 8 to the 2/3 is 4. That's this number. So here I take the cube root of 8 and get 2. I can cancel that 2 into that 2 and leave me with 1/3. That'll give me the approximation on this graph at any point near x is 8. So now we're going to take that point as our x. So now the linear approximation at 8.25 is going to be 4 plus 1/3 of 8.25 minus 8. 8.25 minus 8 is just 0.25, which is 1/4. So it's 4 plus 1/3 times 1/4. So it's 4 and 1/12. So that's the other way you use the linear approximation, using the entire y value and not just the change in y value. Okay, so I mean, they all look like these two. When you read them carefully, and then maybe you can figure out what's going on. So let's use the rest of the time to talk about finding the max and min values of a continuous function on a closed interval. I'll draw a picture. So this takes us to section 4.1. We're looking at something called absolute extrema. Draw your graph that looks something like this. Let's see, it goes up, a little bit down, make a spike in it. Something like that. Right, doesn't have any breaks, jumps, or holes in it, just has a couple of wiggles in it. And one sharp corner. Then let's put the x-axis down here. So this particular function shows a continuous function. And if I leave the arrows on the ends of it, then if I ask you where's its largest value, you say, well, there isn't one because it continues to grow. And same deal here. You can't tell me where the smallest value is because it continues to get smaller and smaller. But if I lop off the ends of this graph, say here, cut that arrow off, and say that that's the ordered pair A, F of A. And then go over here and cut this end off, maybe about right here. And say that that's when X is B. Now, if you compare all the Y values there is a tallest Y value and there is a shortest Y value. There's an absolute maximum value and an absolute minimum value. Looks to me from my picture that this location here is going to be the absolute maximum. It's taller than any of the other tall points on this graph. Of all the tall points on here, that one's the tallest. And of all the low points on here, it looks like this one's the lowest. Agreed? I'm comparing that low point to that low point to that low point. And that one's the lowest. So here's the absolute minimum. The points that I'm comparing it to have places at which the tangent line is going to be either horizontal or where there's a sharp corner and there's no tangent line. So the picture tells me exactly how I'm going to find my largest and smallest y values. I'm going to make a collection of all of the points at which the derivative is either 0 or where the derivative does not exist. Then I'm going to look at the y values, and I'm going to compare the y values at those places with the y values at each end. The largest of that collection of y values will be the absolute maximum, and the smallest of that collection of y values will be the absolute minimum. So, to find the absolute maximum, that's just the largest of all the y values, and the absolute minimum, which is the smallest of all the y values. We collect all x at which, so let me preface this. For a continuous function, continuous, spell for me, C-O-N-T-I-N-O-U-S. Continuous function whose ends are cut off at A and B, for a continuous function on A and B, to find the absolute maximum and the absolute minimum of f on that interval, you first collect all x at which the derivative is 0 or where the derivative does not exist, only in A to B. And then you compare the y values at these points with the y values at A and B. The largest of them will be the absolute max, the smallest is the absolute min. I don't have to compare the y values at every single point. Points like here are not important. I want to know where the graph hits its peaks or its valleys. So I'm only interested where the derivative is 0. And if there's a sharp corner, there would be no derivative. The places on a function at which the derivative is 0 or where there's a sharp corner like that are called the critical numbers of the function. And this entire process we can call the candidates test. we make a collection of our candidates and then compare the y values. So let's kind of start with something kind of easy. Find the absolute maximum and the absolute minimum of f of x is equal to x cubed plus 6x squared plus 9x plus 8 on the interval from x is 0 to x is 10. And while you're writing, do you agree that every continuous function defined on a closed interval is going to have both an absolute maximum and an absolute minimum? Every continuous function defined on a closed interval will attain both an absolute maximum and an absolute minimum. Even if our function is just a horizontal line, as long as it's continuous, it's going to have a largest and smallest point. In the case of a horizontal line, the largest point and the smallest point could be the same, and it'll be every point on the line. But if it's continuous function, it's going to have some sort of tallest and smallest point. If it's not continuous, there's no guarantee, right? If I had an asymptote in here, then one end will probably take off and there'll be no tallest point. But as long as it's a continuous function on a closed interval, it's going to have them both. That was the first question on my oral exam for my master's degree. I had to prove it. And I choked. But that's okay. I'm here today with my degree safely hidden so that they can't take it away. Because it's kind of an obvious thing, right? The picture shows you, just look at all the critical numbers and the two endpoints. Depends on where I cut them off. Had I cut this off, had I cut this one off, say, up here, then that one's going to be my minimum. Just so you have to compare at the endpoints. So compare the endpoints on the graph with all the critical numbers on the graph. So I want you to do that first. Find all the critical numbers. Pretty important name. Because they tell us the cool stuff that's going on to the graph. That is, take the derivative, set equals 0, and solve for x. This is just a polynomial function, so there aren't going to be any sharp corners to it. So you're going to find out where the derivative is equal to 0. And you're only interested in the critical numbers that are between 0 and 10. So if you find some that live outside that interval, throw them away. That doesn't tell us anything about what the question is asking for. You should get two critical numbers, right? It's a third degree polynomial. So you can kind of visualize it. It looks something like that. Go up, down, and then back up. So you should find two critical numbers. What'd you find? Which two critical numbers did you find?
Not any in between.
1 and 3. 1 and 3. Right? Take the derivative. The derivative here is 3x squared plus 12x plus 9. We'll set that equal to 0. And as I do that, I'm going to factor out the common factor of 3. And then I try to factor this. I look for factors of 3, both with the same sign that add to 4. So that'll be x plus 1 and x plus 3. So that's too bad, right? Because none of them are in between 0 and 10. I get x is -1 and x is -3. So neither of these are in the interval. So we throw them away. That means I'm only interested in the value of the function on the endpoints. Okay, so there are no candidates for extreme values in between 0 and 10. That means one of these is going to give the max and one is going to give the min. So we just find f at 0. That'll be 0, 0, 0, 8. Then f at 10. 10 cubed is 1,000. 10 squared is 100. Times 6 is 600. 10 times 9 is 90. So I'm, pretty confident this one right here is my maximum. This one's the absolute min. This one's the absolute max. So now let me change the instructions. I want you to determine the absolute max and min of this thing on the interval, say, from -10 to 0. So part B, do the same, but on the interval from -10 to 0. So all that stuff with finding the critical points, we keep both of those. So I'm just gonna do this in table form. I'm gonna compare the y values at x is -1, x is -3, x is 0, and x is -10. And I'm comparing the y values. They're going back into here, into the x cubed plus 6x squared plus 9x plus 8. All right, so I'm putting -1 in here. -1 cubed is a -1. Squared, I get a +1 times 6 gives me 6. This gives me a -9, and then add that 8. So I have a -10 and a +14. Looks like this y value is 4. Now I'm putting the -3 in for x. -3 cubed is a -27. Squared, I get 9 times 6 is 54. -3 times 9 is a -27, and then plus 8. So 27 and 27 is 54, so out of here I get 8. We already did f of 0. F of 0 was also 8. And now let's check f of -10. -10 cubed is -1000. Then I get a positive 600 minus a 90 plus 8. So that's a -1090 added to 608. That's going to be a positive. I don't know, maybe a 482. Close. Yep, it would be. So now I'm looking at these y values, I'm comparing 4, 8, 8, and -482. And by a long shot, this is the absolute min. And there's a tie for the absolute max. It's going to be 8. Okay. Is there time for another? Is today a short day or a long day?
Short.
Is our short day? Well, our short day then is over. We'll do more of these on Wednesday. Okay, so I'm shooting for our test through this section. Through section 4.1. We'll look at 4.2. We might want to put that on there. We'll look at it. But our test is 1 week from Wednesday, so I'll let you guys decide. Right, 1 week from this Wednesday. Right, 1 week from our next. 1 week from. 1 week from this Wednesday. Okay, let's bring it on. You guys have wrote stuff on paper. Riley, Tammy, Jordan, Cassie, here's your papers. And I'm going to put my thingy away. Let me cut this off.